When conjugated dienes undergo electrophilic addition reactions, you get two products. You get what we call the kinetic product that is formed faster or more rapidly, and the product that is most stable. We call that the thermodynamic product. And it's summarized in here. So there's a conflict here between stability and rate, the reaction rate and stability. This may not be common for many organic reactions because in most cases, the most stable product is the one that is formed faster. This is the best scenario that we look for when running organic chemical reactions. However, this may not happen in this lecture, especially with conjugated dienes. You may, in this case, get the kinetic product and not in high yield and the thermodynamic in a low yield. Or if you alter the conditions, you can get the thermodynamic product in high yield and the kinetic product in low yield. So if you pay attention to this right here, you'll notice that the 1,2 addition is your kinetic product. And if you notice the temperature here, it's 80 degrees below zero, negative 80. So this favors the kinetic product. So if we have this, you would get 80% yield and 20% for the thermodynamic. So let's actually label this. This is the kinetic product, the 1,2. And this is the thermodynamic product. So again, this is formed faster, and this one is most stable. And the reason why it's most stable is, if you recall from organic one, there's a lot of concepts that you actually have to remember from organic one. Luckily, I'm going to ask you to review specific ones, of course, not every single thing. If you look, this alkene along the double bond has 2 H's on it and 2 carbon atoms. They're right here and right there. Whereas this one has only 1 carbon atom. It's right there, and 3 H's. So the more substituted around the double bond, substituted double bond, the more stable it will be. Very well, let's look at the effect of the temperature here. If we alter now this to 40 degrees Celsius, we get 15% for the kinetic, the 1,2 addition, and 85%, a huge difference for the thermodynamic. So this will be your major product. And of course, it's the more stable, the most stable. To explain this, we need to look at the energy diagram. Now, I'm going to do my best explaining as much as I can using the points underneath, but we may need to draw some things here. Number one is be aware that you're starting with the same reagent. So you have the HBr and the conjugated diene. So the transition state, the first step, so this is the first step for both products. However, we're going to label, this is our 1,2 product. And here's the transition state for the 1,2 product. And there's a transition state for the 1,4 product. So if you recall from organic 1, I'm going to use a different color here. This would be EA for the 1,2 product. And then this, let me just bring this. This would be the EA for the 1,4 product. Very well. Notice that EA for the 1,4 product is larger than the EA, the activation energy, for the 1,2 product. So I'll give you a minute to take a few seconds to take a look at that and compare them. So let's explain here. It says at negative 80 degrees Celsius, there isn't enough energy for the reverse reaction to occur. Therefore, the product that forms fastest, the one with the smallest EA, will predominate. So if you notice here, there isn't enough. When you get to this intermediate, you can't simply go back and make this reaction reversible. So it has to go with the faster route, and that faster route is with a smaller EA. At 40 degrees, there is enough energy to reverse the reaction to take place, and that can revert back to the common intermediate. So if you have enough energy, you can go back to the intermediate, and the intermediate can undergo a resonance structure where it forms a carbocation for the thermodynamic product to form. So this is just here more explanation is that you need more energy in the form of temperature, kinetic energy, to make the reaction reversible to the intermediate here to, again, make the thermodynamic product. If you don't have enough energy, the kinetic product will predominate. The question is, why is the 1,2 product formed rapidly? And you'd have to look at this. This is in your book, and it is called the proximity effect. So if we show you a mechanism of this, is that if this attacks, and if we have an HBr here, that's why mechanisms are very important. That we would get the following. So the H is added here, and then we have a Br in proximity. So I'll add the H so you can say, where did it go? Of course, there are 2 other H's on here, but here's the Br. So if you look at this, the Br, the bromine, the bromidimine, is close to the carbocation. So bromide is close by to carbocation. And we call this the proximity effect. So that's why it forms. And this video marks the end of the conjugated dienes in these kind of reactions. What I mean by this is where you have the kinetic and the thermodynamic control. What's going to come next is another reaction of conjugated dienes, but it has its own name. It's called the Diels-Alder reaction. So we tend to isolate Diels-Alder from what we did here.